Welcome to the Deep Dive, where we dig into the latest AI and tech papers to pull out the really important stuff. Today, we're looking at something kind of fundamental, almost invisible, that powers a lot of modern AI and scientific computing. It's called automatic differentiation, or AD. Think of it as the engine under the hood for training those huge AI models, but also for running complex scientific simulations. And our mission today is to get into a paper called DaCe AD, Unifying High-Performance Automatic Differentiation for Machine Learning and Scientific Computing. We want to figure out how it tackles some really persistent challenges and apparently delivers some pretty incredible speedups, making AD potentially much easier for you, whether you're deep in AI research or an ML engineer trying to get things done.
Yeah, this paper introduces DaCe AD. It's essentially a new engine for calculating gradients automatically, which, as you said, is just critical. For training AI models, sure, but also for these really complex scientific codes. The big problem it's trying to solve is that, well, current tools often cause headaches. They might force you to rewrite code, or they only work with one language like Python, or they're just slow, especially on scientific code, or they eat up way too much memory. Scientists often end up just coding gradients by hand. It's painful.
Wow, okay.
DaCe AD's big promise, its breakthrough really, is that it works with the code you already have. Python, PyTorch, ONNX, even Fortran, no changes needed. And it's smart about balancing memory use and computation to be really, really fast.
Okay, how fast are we talking?
The numbers are pretty staggering.
Yeah.
Average speedups of over 92 times compared to JAX, which is, a major Python framework across a set of scientific benchmarks. And in some specific cases, up to 2,700 times faster.
Wow. Okay.
Right. It means scientists, ML engineers, you could potentially unlock AD's power without all the usual pain points. Accelerating discovery. Imagine simulating molecular interactions. What took days might take an hour. That's the potential here.
That really paints a picture. Okay, let's back up a tiny bit for everyone. What exactly is automatic differentiation? Lay it out for us.
Right. So fundamentally, AD is a collection of techniques. Its job is to calculate precisely how a function's output changes when you tweak its inputs. Think of it like a super complex machine with tons of knobs. AD tells you exactly how much turning each knob affects the final output. And it does this systematically, using the chain rule from calculus, basically. It avoids manual math, which is error-prone and tedious, and it's way more accurate than just guessing or using numerical approximations.
Perfect feedback, essentially.
Exactly. Perfect feedback on every little adjustment.
And why is getting that precise feedback, those gradients, so critical right now?
Oh, it's absolutely central. In machine learning, it's the core of backpropagation. That's how neural networks learn. Without efficient AD, you just wouldn't have today's large language models, period. Updating billions of parameters, that relies entirely on AD, but it's huge in scientific computing too. For sensitivity analysis, like how much does my climate model output change if this input parameter shifts slightly? Parameter estimation, data assimilation, and weather forecasting, oceanography, fields where small changes matter a lot. And we're seeing this growing trend, right? ML models getting integrated into scientific simulations, which makes having a tool that bridges both worlds, like DaCe AD aims to, even more important.
Okay, so it's powerful, it's essential, but you mentioned the headaches earlier. If it's so great, why isn't everyone using it seamlessly? The paper lays out some big limitations with the current state of things.
Yeah, exactly. The paper highlights 4 main hurdles. First is limited language support. Tools like JAX or PyTorch, mostly Python, Zygote, that's Julia. So if you have a project using, say, Fortran for the heavy simulation parts and Python for analysis, you're stuck maintaining maybe 2 different AD systems. It's complex.
Okay, that makes sense. And that ties into the second point about needing to change your code.
Right on. Code modification requirements. That's a big one. Many frameworks make you rewrite your code to fit their way of doing things, like JAX with its immutable arrays. You can't just do AI00. You have to use their specific syntax, like AAETI.set0. It seems small, but imagine you have a massive validated Fortran code from 20 years ago. Rewriting large parts of it just to use an AD tool. That's a huge barrier. It slows things down, introduces risks.
So you're not just a climate scientist anymore. You also need to be an expert in the quirks of JAX's array handling.
Pretty much. Yeah. And that's the third limitation, the performance optimization burden.
Yeah.
The frameworks often leave it up to you, the domain scientist, to figure out how to make the gradient computation actually run fast. That's a whole different skill set.
Okay. And the last one, something about memory.
Yes, the rematerialization problem, related to naive memory handling. Most tools default to a store-all strategy. They save every intermediate value calculated during the forward pass, just in case it's needed for the backward pass gradient calculation. For big, complex simulations, this can mean needing absolutely enormous amounts of memory. Often the tool just gives up and pushes the decision back to the user. Okay, you figure out what's cheap enough to recompute instead of store.
Right. So for you, the person actually trying to use this stuff, it all adds up. Limited languages, forced code changes, you have to optimize it yourself, and you might run out of memory. It makes applying AD to complex science really hard, often pushing people back to manual derivatives, which, as you said, is slow, error-prone, and a maintenance nightmare.
Okay, so this sets the stage perfectly for DaCe AD. The paper claims it solves these issues without requiring code rewrites. That zero code rewrite claim is huge. How does it actually pull that off?
It really comes down to its foundation. DaCe AD is built on the DaCe framework and DaCe ML. What these do is take your code, Python, PyTorch models, ONNX, Fortran, whatever, and automatically convert it into something called a stateful data flow multigraph, or SDFG.
SDFG, okay, What is that? Think of it as a really detailed map or blueprint of your program. But it's not just the steps. Crucially, it tracks the data. How data moves between operations, where it's stored, how it gets transformed, even when it gets overwritten in memory. This deep data-centric view is the key. It allows DaCe AD to really understand the program structure. From that SDFG, it can then analyze, optimize, and generate the backward pass code, the gradient calculation, very efficiently. And because it starts from this universal SDFG representation, it can handle all those different input languages without you needing to change your original source.
That makes sense. The SDFG acts like a universal translator and analyzer. So let's dig a bit deeper into the mechanics. How does it handle complex things like if statements or loops using this SDFG?
Okay, good question. A key step is finding the critical computation subgraph, the CCS. Basically, for a given output, what parts of the original calculation actually influenced it. You trace backwards from the output. DaCe AD does this efficiently using a reverse breadth-first search on the SDFG.
But what about IFLs? The path isn't fixed beforehand?
Right, so the initial trace might include both branches of an IFLs. It might overestimate the CCS slightly, but DaCe AD is clever. During the forward pass, it stores the result of the condition, was it true or false? Then, during the backward pass, it uses that stored value to prune the CCS, only keeping the path that was actually executed. It ensures gradients only flow along the correct path.
Ah, okay. Smart.
And there are other subtleties too, like gradient accumulation. If an array value is read multiple times, you need to sum up the gradient contributions. And crucially, gradient clearing. If you overwrite a value in an array, like AI, is correctly reset or cleared before new gradient contributions are added. DaCe AD handles this automatically based on the data flow graph.
Okay, and loops. You mentioned they are often a pain point for other AD tools.
Definitely. Fully unrolling loops is often infeasible. It blows up code size and compile time. DaCe AD aims to generate compact backward loops that mirror the forward loops efficiently. It focuses on well-structured loops, affine loops, predictable iteration spaces, no mid-loop breaks or continues. For sequential loops, conceptually, it's like understanding the data dependencies across iterations, figuring out the critical path within the loop structure, and then generating a new reverse loop for the gradients. But it uses sophisticated data flow analysis on the SDFG to achieve this without actually unrolling the loop, which is key for performance.
And parallel loops.
Parallel loops, represented as maps in the SDFG, are often simpler because the iterations are independent. If a map is part of the critical path, DaCe AD generally just creates a corresponding backward map to compute the gradients in parallel.
So this data-centric SDFG approach really gives it a fundamental advantage in understanding and transforming these complex structures automatically.
All right, let's talk about that trade-off you mentioned earlier, the store versus recompute dilemma. This seems like a really critical optimization problem. How does DaCe AD tackle it?
Yeah, the rematerialization problem. It's central to reverse mode AD. You need values from the forward pass to compute gradients in the backward pass. Do you store them all? Eats memory? Do you recompute them? Cost time. Most tools either pick a simple default, like store all, or, well, they punt the decision to the user, which is hard.
Right, how do you even know what the optimal strategy is? Exactly,
and this is where DaCe AD does something novel, really innovative. It formulates this entire decision process as an integer linear programming problem, or ILP.
Okay, ILP. Break that down. How does using mathematical optimization solve this? So you, the user, provide a memory budget. Say, my GPU has 8 gigabytes, don't use more than 500 megabytes for storing intermediate values, unquote. DaCe AD then looks at every array or tensor that might be needed for the backward pass. For each one, it creates a binary decision variable. 1 means store it, 0 means recompute it. It also estimates the computational cost if you do recompute it. The ILP solver's job is then to find the combination of zeros and ones, which things to store, which to recompute that minimizes the total recomputation cost, subject to the constraint that the total memory used for stored tensors does not exceed your budget, like 500 MB.
Wow. So it mathematically finds the cheapest way to run, given your memory limit.
Precisely. Let's take the paper's simple example. A0, A1, A2. Maybe recomputedly 0 is fast, A1 medium, A2 slow. The ILP solver looks at the costs, the memory footprints, and your overall budget. In their example, it determined the best strategy under the constraint was to store A1 and A2, but recompute A0 because that minimized the recomputation penalty while staying within the memory limit. And it even handles control flow paths. It makes sure the memory budget holds true regardless of which branch of an if statement is taken at runtime. It considers the worst-case memory usage across paths.
That's incredibly powerful. It automates a really complex, error-prone optimization task, takes the guesswork out.
Completely. It lets scientists focus on their science, not on intricate memory management heuristics. And solving the ILP itself is usually very fast, like milliseconds.
Okay, so the theory sounds great. The ILP approach is smart. But does it deliver in practice? Let's talk about the performance evaluation against JX using NPBench. What did they find?
All right, the rubber meets the road. They used the NPBench suite, which has a good mix of scientific and ML-style kernels, ran it on Intel Xeon CPUs, and carefully validated the gradient results. The headline, DaCe AD was faster than JAX on 38 out of the 52 benchmarks. The average speedup was huge, 92x. Though the geometric mean, which often gives a better sense for typical improvements, was 4.1x, still very significant.
Interesting. And you mentioned earlier the performance differed based on the type of program.
Yes, that's a key insight. For vectorized programs, ones using whole array operations, common in ML days, AD was faster on 8 out of 12, average speedup around 1.4x. Here, both frameworks rely on optimized libraries like MKL or CubeLAs, so the differences are smaller. But for non-vectorized programs, the ones with explicit loops, maybe complex control flow, accessing individual array elements, very common in scientific code, that's where DaCe AD really pulled ahead. Faster on 20 out of 26 with that massive average speedup of 134x and a geometric mean of 7.12x.
Okay, 134x average speedup on those loop-heavy codes. Why such a dramatic difference there? What is JX struggling with that DaCe AD handles better?
It comes back to those limitations we discussed. First, code modifications. JX often requires substantial changes to make standard scientific code work using jax.numpy, handling immutability with ati.setSummo, sometimes wrapping loops in jax.lax.scan. This isn't just inconvenient, it can impact how JX optimizes the code. Second, dynamic slicing overhead. JAX translates array indexing like AI, J, into internal function calls, lax.dynamic slice, which have overhead, especially inside tight loops. DaCe AD via the SDFG often generates direct memory accesses, which are much faster. Third, the cost of immutability. A simple update AI in the forward pass can force JX to create large temporary arrays in the backward pass to handle gradients correctly. DaCe AD's stateful representation understands overwrites and can often manage gradients more efficiently with single writes. And finally, bound checks. JX sometimes inserts runtime checks for array bounds in the generated backward pass code. DaCe AD tries to prove these bounds are safe at compile time using the SDFG, removing the runtime overhead.
Got it. So those seemingly small framework differences add up to enormous performance gaps in loop-intensive code, which brings us to that Cytosync example with the incredible 2700x speedup. What's going on there?
Well, see, Cytosync is a great case study. It's basically a 2D stencil update. Each point is updated based on its neighbors repeated over many time steps within a loop. Classic scientific pattern. For JX, running this involves all those issues we just mentioned, inside the innermost loop, the dynamic slicing, the immutability forcing array copies, the runtime checks. It adds up incredibly fast. Especially the immutability means it might create a whole new copy of the large NXN array for every single element update inside the loop, potentially millions of times. DaCe AD, on the other hand, analyzes the SDFG. It understands the in-place updates, generates efficient code with direct memory access, performs checks at compile time. It essentially generates a backward pass that mirrors the forward pass structure efficiently. The result. On the tested hardware, DaCe AD computed the Cytosync ticket gradients in 1 second. JAX JIT took over 47 minutes. That's the 2724x speedup.
1 second versus 47 minutes. That's just astounding.
It really is. Now, to be fair, for very small array sizes, JAX's overhead might be lower, and it could be slightly faster. But for any reasonably sized scientific problem, DaCe AD's approach scales much better. And interestingly, this advantage held even comparing to DaCe AD on CPU to JAX on GPU for this specific problem. DaCe AD CPU was still 275 times faster than JAX JIT GPU, highlighting that the algorithmic efficiency gained to the SDFG analysis was the dominant factor here, more so than raw hardware power.
Okay, so we've seen the performance. Let's quickly revisit that ILP checkpointing. Did the experiments show that automated store recompute strategy working effectively?
Yes, they did. They showed results where, for a given memory budget, like 500 MILB in the example, the ILP solver automatically made the optimal choice in that case, storing A1 and A2, recomputing AO. This resulted in the fastest execution time possible while respecting the memory constraint. It demonstrates that the automated system works and frees the user from having to manually figure out these complex trade-offs.
That automation is really key for usability, especially for domain scientists.
Absolutely.
So, putting DaCe AD in context, how does it stack up against the wider landscape of AD tools, both old and new?
Well, historically, you had tools like Ada4, Tapenade, often focused on Fortran 77. Very important, but language-specific. Then came the modern ML giants, PyTorch, TensorFlow. Highly optimized for neural networks, but as we've discussed, they have limitations for general scientific code handling in-place updates, the store-all memory issue, sometimes poor performance on non-standard patterns. PyTorch's Torch.combo with AOT Autograd is improving, but it often relies on recognizing specific operators rather than analyzing general arbitrary code like DaCe does through the SDFG. There are also other modern general AD tools. Enzyme AD is notable, works on LLVM IR, so it supports C, C++, OAuth, Fortran, Rust, etc. That's great generality. But performance optimization is often manual, and its checkpointing, while it exists, is heuristic, not based on a constrained optimization like DaCe AD's ILP. Zyga for Julia is powerful, but again, often requires rewriting code into Julia and defaults to store all. And there's prior research specifically on checkpointing, like Checkmate, which also used ILP but could have scaling issues, or Revolve, optimal for simple loops but with strict assumptions. DaCe AD's ILP approach targets array containers within general SDFGs, making it applicable to more complex computational structures.
So DaCe AD seems to carve out a unique space by hitting that sweet spot. Generality across ML and science, high efficiency through SDFG optimization, and this intelligent, automated handling of the memory compute trade-off, all without forcing code rewrites.
That's really the key takeaway, yes. It aims to bridge those gaps.
Okay, so this deep dive into DaCe AD really paints a picture of a powerful, potentially transformative tool, especially for anyone working where HPC, scientific simulation, and machine learning overlap. That ability to get optimized gradients without touching your original code, that's a huge leap forward.
It really is. And it makes you wonder, right, as we see more and more AI, more machine learning being embedded directly into complex scientific models, think climate, material science, drug discovery, how will tools like DaCe AD, tools that can unify these different worlds and automatically handle the underlying complexity of differentiation and optimization, how will they change the actual pace of scientific discovery? What breakthroughs become possible when you remove these kinds of fundamental bottlenecks?
The provocative thought indeed. What complex problem are you, the listener, working on where this kind of seamless, high-performance automatic differentiation could make a real difference? We hope this deep dive gave you some valuable insights into DaCe AD and the evolving world of automatic differentiation. Thanks for joining us. Until next time, keep exploring, keep questioning, and keep diving deep.